Alright, so in this video, we'll be looking at one of the two major types of calorimetry. And so really, there are two types of calorimetry that we'll be exploring in general, right? So calorimeters or calorimetry. And so there are going to be two types that we'll be exploring, right? The first one is going to be constant pressure calorimetry. And the second is constant volume calorimetry. And so in the case of constant pressure calorimetry, we would be using what is called a coffee cup calorimeter. A coffee cup calorimeter. And in the case of constant volume calorimetry, a bomb calorimeter would be used. Bomb calorimeter. And so in this video, we'll be looking at the first type, the constant pressure calorimetry, using a coffee cup calorimeter, and we'll be looking at constant volume calorimetry in another video. But on this subject of constant pressure calorimetry, it's for processes that take place at constant pressure that, the heat transferred, denoted QP. Q is the symbol that denotes heat, and we're saying Q sub P because this is the heat at constant pressure. And so this heat that's transferred, this Q sub P, is going to be measured in a coffee cup calorimeter. And so this is a pretty simple apparatus that is common in Gen Chem labs, AP Chem labs, and it can be used to find the heat of an aqueous reaction, right? The heat, for example, that can accompany the dissolving of a salt. And you can even use it to find the specific heat capacity of a solid that doesn't even necessarily dissolve in the water. But before we move any further, let's just look exactly what this apparatus of a coffee cup calorimeter is actually made up of. And so, well, firstly, as the name would suggest, a coffee cup calorimeter is composed of a coffee cup. Well, more specifically, it's going to be a styrofoam cup. And the reason that we use styrofoam is because it is what is called a good thermal insulator. And what that means is that this cup made of styrofoam, because of the material styrofoam, it is going to, for the most part, prevent one, the loss of heat from inside of the cup into the environment, and two, the entry of heat from the surroundings into the cup, both of which would interfere with what we are trying to measure, right? The heat of the reaction or heat of the solution. And so because because of this ability to prevent the entry and loss of heat, it is called a thermal insulator. And in fact, in order to further increase this thermal insulation, you may also see two styrofoam cups stacked in order to, again, just further prevent the loss and entry of heat. So you may have two styrofoam cups stacked in this manner as well. But in any case, we're going to have this styrofoam cup, this coffee cup, that's also going to be filled with a solution, let's say water, and let's say we're trying to find the heat of the solution, so we're dissolving the NaCl, salt NaCl, right? And so remember, we're using these for processes that are that are occurring in an aqueous solution. So any sort of aqueous reaction is commonly what we're going to be seeing with these coffee cup calorimeters. So in this case, we're trying to measure the heat of reaction, or heat of the aqueous reaction that occurs with the dissolution, or this NaCl dissolving in water. And so, well, if we want to do that, we're going to need to also have a thermometer. And that's because this change in temperature that accompanies the reaction is one of the main pieces of information that we're going to be able to use, or that we're going to have to use, in order to figure out the heat of the reaction or heat of the solution. And so we're going to need to have this thermometer here to measure the change in temperature of the solution. Additionally, you're going to have a stirrer. And so this stirrer, again, as the name would suggest, is going to be stirring this solution around throughout the reaction or throughout the process in order to, well, one, uniformly distribute that heat, allow for the reaction to, again, or the salt to be uniformly distributed throughout the solution, a number of different things. And so we're going to have this stirrer also in place. And finally, this entire thing is going to be sealed. It's going to be sealed or covered. And again, that's because it's important that we're not allowing heat from the environment or the surroundings to enter and heat from this cup to exit. Because remember, we're trying to measure this temperature, and any heat that leaves or any heat that enters would interfere with the accuracy of this measurement of temperature that we're relying on from our thermometer. So this is generally what this coffee cup calorimeter exactly entails. So now let's look at a practice problem to see what kind of problems we can expect regarding coffee cup calorimetry. So, looking at the problem, we see that you place 50 milliliters of 0.5 molar NaOH in a coffee cup calorimeter at 25 degrees Celsius and add 25 milliliters of 0.5 molar HCl also at 25 degrees Celsius. After stirring, the final temperature is 27.21 degrees Celsius. And we're told to assume that the total volume is going to be the sum of the individual volumes, right? That's 50 milliliters and 25 milliliters. And that the final solution has the same density, and two, the same specific heat as water. And so we're provided with those values, the specific heat of water and the density of water. And so we're going to have to try to find two things in this problem. Firstly, we're going to try to calculate the heat of solution. Remember, this Q means heat, and we have a subscript SOLN, solution. So we're trying to find the heat of solution in joules. And secondly, calculate the change in enthalpy, that delta H. Delta refers to change, and H is our symbol for enthalpy. And so we're trying to find this change in enthalpy of the reaction in units of kilojoules per mole of the water formed. All right, so let's start with the first step. Well, basically what we're going to have to do when we're starting the first problem, right, or the first part of the problem, finding the heat of solution. Whenever we're trying to solve for heat in this type of way, we're going to have to use a very common equation, which is heat Q is equal to mc delta T. It has a nice flow to it, which is kind of why students don't have trouble remembering it. Q is equal to mc delta T. It flows pretty well, but in any case, the m in this case, or we're solving for our heat Q, and the m is going to be the mass. C is going to be our specific heat, which in this case, our specific heat capacity, which in this case is going to be that of water. And our delta T is going to be the change in temperature of the solution. And so by multiplying these three values together, we will be able to find the heat of solution. All right, so well, if we need the mass, we're firstly going to need to, well, how we're trying to find the mass? Well, we need to go from our volume in milliliters to mass in grams, and we can do that using our density, right? Let's see how that would work. Well, firstly, we're looking at the total mass, so we're going to need to calculate the total volume, which we're told to assume is just going to be the sum of the two solutions. So that means that our volume is going to be 50 plus 25, or 75 milliliters. 75 milliliters. And well, since the density is given to be 1 gram per milliliter, if we set this up stoichiometrically, we can see that this 75 milliliters of solution with a density of 1 gram per milliliter, well, we can cancel out our units of milliliters, giving us an answer of 75 grams. And so this is going to be the mass of our solution. This is going to be our M in this problem. So let's just clear this up and take note of that value over here. So our M is going to be 75 grams. We already have our C, right? Our C is the specific heat capacity of water, is just 4.184 joules per gram times degrees Celsius. And well, now we need our delta T. Our delta T. How do we find delta T? Well, our change in temperature, this delta T, is just going to be our final temperature minus our initial temperature. And so in this case, our final temperature was, we were told, was 27.21 degrees Celsius. And from that, we will subtract our initial temperature of 25 degrees Celsius, giving us an answer of 2.9 2.21 degrees Celsius. So this 2.21 is going to be our delta T. All right, well now we can just plug all of this into our equation, or Q equals mc delta T, and we can see that we get Q is equal to 75 times 4.184 times 2.21, right? And this is equal to 693 joules. And we get our units of joules because as we multiply everything out, the other units will cancel out, right? And so again, I guess to demonstrate that, you can see that we're multiplying grams times joules over grams times degrees Celsius times degrees Celsius. And so our grams and grams and our Celsius will cancel out, leaving us with units of joules. So this here is going to be our Q, and our heat of solution. And so it's important that you keep your signs in mind, though. What I mean by signs is like, your positive or negative. So in this case, our heat of solution, right? This is specifically the heat of solution. This heat of solution is going to be a positive value. And the reason is because our temperature, we can see, of the solution is increasing. We're going from 25 degrees Celsius to 27.21 degrees Celsius. And so it is because the solution's temperature increased. In other words, the solution absorbed heat, right? That means this reaction between NaOH and HCl released heat into the solution, into the solution, causing it to increase in temperature, where our heat of solution is going to be positive with respect to this solution, right? But our heat of reaction, on the other hand, the reaction is giving off heat. It is losing heat to the surroundings. So if we were trying to find our heat of reaction, well, that value would be negative. And so an important relation then comes into play, right? Our heat of solution is going to be equal to negative our heat of reaction. So in case, if this value was positive, let's say that this was, our reaction was taking in heat from the solution, from the environment, from the surroundings, this value would be positive, and it would be negative. The negative of a positive is going to be negative, so our heat of solution would then be negative. So these two are just going to be opposite signs. They're equal in magnitude, but opposite in sign. So it's just important that you keep in mind what it is that we're looking at, whether we're looking at heat of solution or heat of reaction. Are we increasing in temperature? Are we losing heat? Are we, keeping those things in mind and keeping our sign, then the appropriate sign, in mind. So anyway, our answer for part 1, this heat of solution in joules, is going to be 693. So let's just clear up some room and look at the second question, or the second part of this question, right? We're now trying to find or calculate the change in enthalpy of the reaction in kilojoules per mole of water formed. So if we're trying to find, again, we see in the problem we're trying to find per mole of water formed. So let's first just find how many moles of water were formed or were produced. And the reason we're doing that is because this change in enthalpy in terms of kilojoules per mole of water formed, right? We're going to have to divide, or rather the way that this works is we're going to be taking our heat of reaction, right? It's the heat enthalpy of the reaction. So we're going to be having to look at the heat of reaction divided by the number of moles of water in this case. Right? It's by moles, but in this case, moles of water, right? It is kilojoules per mole. We calculate this, or we measure this Q of reaction in units of kilojoules, and our amount of water is in moles. And so this change in enthalpy is going to be found in this way. And so we already know our Q of reaction because, well, we know that this Q of reaction is this negative our Q of solution. And we just calculated this Q of solution just earlier to be 693 joules, and so our Q of reaction is just negative of that, negative 693 joules. So now we just need to find the number of moles of water that we're producing. So in order to do that, let's first look at the reaction, right? The reaction in play here is the one occurring between NaOH and HCl. So writing out the balanced chemical equation for this would be NaOH, which is reacting with HCl. And well, that is going to give us NaCl plus H2O. And so if this is the reaction that is occurring, these are our reactants and these are our products, well, how do we find how much water we're forming? Well, remember, whenever we're trying to calculate something of that nature, we have to always first figure out what the limiting reactant is, because that limiting reactant is going to determine how much product we are forming. And so, well, we're told that we have 50 milliliters of 0.5 molar NaOH. So, well, that means we have, well, 50 milliliters is just going to be, if we have to convert that to liters, it's going to be 0.05 liters, right? Because remember, our molarity, or M, is just moles per liter. And so we need to convert our volumes to liters when we're doing this. And so, well, if we have 0.05 liters, we will just go from 0.5 moles per liter, right? That's our molarity of NaOH, times 0.05 liters. And so, well, that cancels out, giving us an answer of 0.025 moles of NaOH. Now, doing a similar thing for our HCl, well, we also have, well, we have 25 milliliters. We have 25 milliliters in this case, which if we convert to liters is 0.025 liters. And so setting up a similar stoichiometric setup as we have here, this is also going to be 0.5 molar, so it's 0.5 moles per liter times 0.025 liters, giving us 0.0125 moles of HCl. And so we can see that clearly our HCl is going to be our limiting reactant here. And so taking that into consideration, we can now calculate how much water we're forming. Well, because we see that we have 0.0125 moles of HCl, and according to our balanced chemical equation, we see that for every 1 mole of HCl, we form 1 mole of water. So for every 1 mole of HCl, we get 1 mole of H2O, or water. And so we know that we will be forming 0.0125 moles of water from this reaction. And so since our limiting reactant is HCl, and we see that we have a 1-to-1, so for every 1 mole of HCl that reacts with NaOH, we will form 1 mole of water. Setting this up in this stoichiometric fashion, we can find the amount of water that we form in moles. And so now that we've got that number, we can simply plug it into our change in enthalpy formula we just spoke of earlier. Or if we just to remind ourselves, this change in enthalpy is going to be our heat of reaction divided by our moles of water in this case. And we found our heat of reaction, right, is negative, our heat of solution, divided by moles of H2O. And so that's negative 693 joules over 0.0125 moles. Well, if you remember, one small thing that we're missing here is the fact that we're trying to find our answer in kilojoules per mole. So if we left this in this way, that would give us the wrong answer. So let us first, before moving any forward, convert our 600 or our negative 693 joules into kilojoules. And we can do so simply by saying the fact that we have, for every 1 joule, we have 1,000 kilojoules. Oh, excuse me, sorry. Every one, that's my bad. Every 1 kilojoule has 1,000 joules, and so by canceling out our units of joules, we get our answer of 0.69, negative 0.693 kilojoules. So now, simply plugging this value, negative 0.693 kilojoules per 0.0125 moles gives us an answer of negative 55.4 kilojoules per mole. And this here is going to be our answer. This is our change in enthalpy of the reaction. So I'm hoping that made sense. This is generally the type of problem, or a very common type of problem, that you can expect to see when it comes to coffee cup calorimetry. So it's just important that you, again, know how to find your heat of solution and make the distinction between heat of solution versus heat of reaction, which is just going to come down to whether it's a positive or a negative value. So just be conscious of the situation that's occurring, whether you're raising your temperature or decreasing temperature. So keeping those things in mind, you can identify your heat of solution versus heat of reaction. Again, just keep in mind the formula for your change in enthalpy in this case, and you should be fine. Also, one last thing is always keep in mind the units. In the earlier part A, we were told to find our answer in joules, whereas in the second part, it's kilojoules per mole. So just always remember to keep in mind the units that we are trying to, or that we're asked to find the answer in. Otherwise, it's just unnecessary points to lose. So, in any case, I hope you got some value out of this video. That brings us to the end. Again, if you did, please show your support by liking and subscribing and leave in the comments what you would like to see next. And I'll see you guys in the next one.